All right. Thanks, Colin. Thanks, Louis, and for giving us a preview of the ST-Sim. I really enjoy watching it every time I see bits of the model. I learn more things. It's fabulous. So, hi everyone. Anna Richards here from CSIRO. I'm just going to give a very brief run through of a case study that we just worked through during some training we did with Colin and Louis a few weeks ago. I mentioned this in the talk that I gave on Tuesday, so I won't go into some of the details that I went into on Tuesday, and that recording will be available if you missed it on Tuesday. So I'm just going to provide an introduction to this forest icon site that sits on the Murray River about northwest of Melbourne. It straddles the New South Wales and Victorian borders. So on the northern side of the river, we have Gunbower-Koondrook-Perricoota State Forest, which there's timber harvesting that occurs in that state forest, and it's managed by Forestry New South Wales. And then on the southern side, on the Victorian side, we have Gunbower State Forest and Gunbower National Park. And both of these areas are Ramsar sites. The GKP area, which I'll call it now for short, is being used as a case study for an ecosystem accounting project that I mentioned in that previous presentation. I won't go into that, except as part of that case study, we developed up some state and transition models, which we've been using with Colin and Louis as an example of how you might apply the ST-Sim to a landscape like this. So probably one of the key drivers of changes in the landscape at GKP, other than the timber harvesting that I mentioned, has been river regulation and water extraction from the Murray, which has led to a reduction in the frequency and duration of flooding across the icon site. You can see the actual flooding rates there in orange versus a simulated flood regime if there was no river regulation in the blue. And there's also been a shift, it's a bit harder to tell on the graph here, but a shift in the seasonality of when that flooding occurs from a winter spring to a spring summer. These are the main ecosystems that can be found across that floodplain at GKP. One of the majority of the ecosystems that sit within what we call an archetype, and I've gone into that in the other presentation. So apologies about some terms, and please ask a question if they don't make sense. But if you can think of it as an ecosystem type, it's the inland floodplain, eucalypt forests and woodlands ecosystem type. So these are red gum and black box forests and woodlands across the floodplain. There's a number of other smaller ecosystem types, including the river itself, of course, but we won't go into those in the case study. One thing I did want to note is that there are small areas of wetlands dotted across GKP. They're very significant in terms of their habitat value for water birds and so forth. And there is a dynamic between the floodplain eucalypt woodlands and forests and the wetlands, and this is captured in the state and transition model. So it's important to understand that. And this is I feel like a naturally occurring dynamic, although it has been modified due to river regulation, where you can switch between these two ecosystem types. This is the state and transition model that we've been using. This isn't the full model, this is just a single state, and there's quite a number of these that sit within the state and transition model. Within these states, we have a number of what we call expressions, which just tells us gives us an indication of the variability within that state over space and time as a result of disturbance and recovery processes, in this case, flooding and drying processes. So you can see these boxes that I have, there's some bold text in them, and that's probably the main thing to focus on. They're the names of the expressions. So you can see the dark green box in the center there is the dominant expression across this landscape. So most of the time when you're at GKP, many of the places you'll visit will look like a mature floodplain eucalypt forest and woodland. And that will have a range, you might have a range of dominant species. If you're closer to the river, you might get larger red gum trees. If you're out on the edges of the floodplain, you grade into a black box system. And the same with the understory, you'll see a more flood dependent understory closer to the river, and as you grade away, a more grassy understory with declining moisture. But you also might see a dense pole stage eucalypt stand, which has very sparse understory. Dense seedling eucalypts when a recruitment event occurs, often after episodic flooding. And a reduced tree canopy expression, which occurs usually when you have a accumulation of stresses such as low rainfall, reduced quantity and quality of groundwater, and also occur when you have insect outbreaks. So this is where the thinning of the canopy, overstory canopy occurs. You can also jump out into an expression which we've called wetlands here, which sits in another ecosystem type, and through prolonged flooding of any of these expressions, you can move into that box. And there is also under extreme dry periods, you can also move into a manifest as a tussock grassland or chenopod shrubland. This hasn't been observed in recent times in GKP, so we don't tend to focus on that tussock grassland or chenopod shrubland element of the model. So this is, I should have mentioned the reference states. This is our best understanding of the disturbance and recovery processes of states across the GKP landscape that have good condition or good habitat for biodiversity. And they might look like this, so that model is quite high level. It captures things that might look quite different, but have the same disturbance and recovery dynamics. So on the left is a red gum forest, on the right is a black box woodland. And we have a number of modified states that are observed across GKP. They have the similar, so you'll see that the boxes look quite similar and that dynamic looks like quite similar, but there's some small differences that I'll point out now. In the modified state called reduced tree canopy over invaded understory, the dominant expression is that reduced tree canopy that's thinned compared to a mature floodplain eucalypt forest and woodland. It's often a result of logging, but it could also be low rainfall and inadequate flooding, reduced groundwater, insect outbreaks and grazing as well. And there's often, there is invaded species in the understory in this expression. That's the key one I wanted to point out for that modified state. And it might look like these photographs here. In the second modified state, the dominant expression is that mature floodplain eucalypt forest and woodland, but it has an invaded understory. So that's the key difference between the reference and this state. And it might look like that. And then the last one is quite distinctively different, the third modified state, and that's the halophytic state. And it's a result of salinisation through rising water tables as a result of excess irrigation in the agricultural areas around GKP. It has a number of different expressions. There's a seedling eucalypt expression, there's a reduced tree canopy expression similar to the other states, but the dominant expression is an invaded halophytic shrubland. And this will look somewhat like that. And this is taken from Gunbower-Koondrook-Perricoota, see states like that. So you can see there's a number of expressions that are common across the different states. So in some points in space or time across that dynamic, it'll be difficult to distinguish if you were on the ground between the different states, but some of those expressions are unique to some of those states. Just to make it fairly complicated, we didn't choose an easy case study for this example, I have to say. But this is trying to make it a bit more simple. So I've got rid of all those boxes and arrows and just shown you a sort of an overview of the state and transition model just within that floodplain eucalypt forest and woodland, remembering that you can also move into a wetland ecosystem as well with extensive flooding, and extensive and prolonged flooding. You can see the key drivers of transitions between these states, and these will be between expressions in the states, and I haven't shown that detail here, but it's been captured in the model, is changes in flood regimes and logging and salinisation. So they're really the key things. And then there's also some other stresses around grazing, livestock grazing, and recreational use of the park, camping and four-wheel driving and so on. I did show the nitty-gritty, so here's the nitty-gritty details here. So with these black arrows that are showing the transitions, there'll be different probabilities of transitions between those different expressions within each of those different states, and you also can get a shift out to the wetland states. And I should have said this at the beginning. This is the development of these models was driven by experts, and this is a list of our wonderful experts. I attended a number of different workshops where we asked them to describe these dynamics that occur in the floodplain, both the reference dynamics, and they used a template model to do that, and these the modified ecosystem states in the landscape and their dynamics. And for each of those boxes that I've described in the model, we have a lot of different characteristics. Colin referred to them as state attributes. So, for example, we know quite a lot about the number of the fish diversity in some of the wetland states and the lowland streams. We know a fair bit about some of the waterbird diversity. the woodland bird diversity and the floodplain forests and woodlands and so on. So we can start to unpack some of the these other interesting variables. I might stop there, Colin.
Okay. So our challenge then was to try and, in a matter, so I'll just preface what I'm about to show you with the following caveat, is that we spent one day together with a group working through some of the numbers on this, a little bit more time before that with Anna, and then I spent another day this past week trying to get some more numbers into it. So this is extremely preliminary. I wouldn't think that the numbers mean anything. It's more just how we went about it and how we got a model like this into the software to give you some idea of, the purpose here is to demonstrate what the software can do rather than show you a working model. We set out to try and model all these states and transitions that I'm showing on my screen right now. The details don't matter. Anna went through this, and what we as a group, with some, how many of us were there? It was on our course, maybe 10 or 15 people, went through just trying to estimate in a workshop some of the actual probabilities associated with the reference portion of this. So I'm going to show you that. But our challenge here then was to how to frame this in our software. So what I'm going to do is I'm going to bring up the SynchroSim software with STSim loaded, and I'm going to, I'm not going to really guide you. You're just going to learn by watching a bit about the software. But the first thing we have to do when we're setting up a model in STSim is to create what we call the definitions, which is basically, establish the currency with which we're going to model. And in a state and transition simulation model, that's really defining the states and the transitions that you're interested in. So we have a screen here for the definitions. We started off by, when you open up SynchroSim and STSim, you have a blank screen. It's like opening up Microsoft Excel. There's this worksheet there. It's blank. There's all kinds of menus, but there's nothing built in. It's up to you to define everything. And that's one of the beauties of STSim, is it can work in theory in any vegetation community. So we had to first decide what we wanted to label things. So we have a thing in here called a state class. It has two labels. We labeled it in a state and expression to line up with the terms that Anna was just talking about. And we also created a strata. Remember, I was talking about stratifying your landscape. We stratified it according to those ecosystem types, and we'll look at what those mean. So that was part of what we had to set up here. Actually, time step units, this probably should be year. I forgot to switch that because we're on an annual time step. And so here we define the strata. So these were the broad classes: floodplain, resprouter, streams, wetlands, woodlands. These, recall from Anna's presentation, these are these 1, 2, 3, 4, 5 major, no, these are the states, sorry. These are one above that. These are the archetypes that the landscape is divided into. These are the biophysical boundaries across your landscape. And now generally these boundaries don't change, but you'll see in a minute that you can actually move a cell from one strata to another. But this is what we defined for these. And today we're only going to focus on the model for the floodplain strata, because that's the only one we've worked up so far. And those are the diagrams that Anna just led you through. On the states, we then had to define what our expressions were and our states. So our states were what we showed over here. These 5 major states here are reference, invaded reduced, invaded mature, halophytic. Those were the 4 states that we expect to see within the floodplain strata. And then we had a second strata called wetlands that we didn't model, but we have it in there as a strata. So you can see that those 4 states are represented, 1, 2, 3, and then 4. Those are represented, but anyway, you get the idea. There's 4 of them there. And then we also had to bring in all the expressions that we wish to capture in here. So those end up on a table here where we define those expressions. And then ultimately, the boxes that are possible in your model are the combinations of states and expressions. And here we have a fairly lengthy list to cover all the possible boxes that you might see over in this giant box scenario diagram. Because this is ultimately, we're trying to model all of this as one complete state and transition simulation model for the floodplain strata. So that was the definition side of things. We also had to decide on our transitions, and we just looked across the conceptual model that we were provided with, that Anna led you through, and we came up with a number of these. So some of these are natural processes, episodic flooding, inadequate rainfall, tree growth, and then others are these are anthropogenic, such as grazing, logging, and so on. But this list, again, was just designed to line up with the same processes that were represented in the conceptual model. Once we do that, we can sort of look at, actually here, what the pathway diagram looks like. So what I'm going to show you first is just the diagram. This is the pathway diagram in the software. Just for, if we go back over here, all I'm looking at is this reference state. So that there are, I think, 7 boxes in here, and these are the 7, oh, there's 5, sorry, there's 5 boxes, at least in our representation here. And so this is the model that we developed in a group, in a workshop. And so I'll just lead you through what this model looks like, the numbers we came up with. So we had to estimate some of those probabilities. This is the wrong PowerPoint. This is it here. So it's a little easier to look at these things in PowerPoint. So these are the 5 boxes that I just showed you there. So the transitions that we had tree growth, which moved, just basically aged the forest across from seedling to pole to mature. In the group, we assigned a certain probability for this. Basically, I won't get into the details, but the seedlings move on to poles when they hit age 10, and the poles move on to mature when they hit age 50, but they don't all move at once. There's a certain probability that occurs when we're moving those across. So that's one of the transitions. The next one we modeled was inadequate rainfall, and that just basically moved a particular cell, if it was in a seedling, pole, or mature state, down into this reduced canopy, or sometimes into grassland, shrubland. And again, to estimate these probabilities, this was done in a workshop. You know, if you had literature, or you had historical data, or you had map data, or field data, or traditional ecological knowledge, all of those things can go into estimating these probabilities. There's many, many ways to do it. We took the simplest route, which was to ask a group on a WebEx what they thought it was in 5 minutes or less. And these were the numbers we came up with 2 weeks ago. And so these probabilities have 2 parts to them generally, the way we did it here. I just kept them separate. One of them is the return interval on the event. So people felt that on average, inadequate rainfall happens once every 20 years, so a 20-year event. And when it did occur, there was 1 in 100 chance that a cell that received inadequate rainfall would actually move into this reduced canopy state. And over here, you know, the seedling, it could, with a 1 in 100 probability, become reduced canopy, and with a 5 times greater probability, when there's inadequate rainfall, it could move over to this grassland, shrubland. So this is an example of what we call a branching pathway, where when a certain transition occurs, we can say probabilistically it could go here or here. We don't have to define definitively what we think is the only thing that could ever happen in the model.
Can I add something, Colin? Can you go back, please?
Sure.
something that we assume that weather events, or actually climate events, are regional. So in this case, the 1 divided by 20 for the return interval is something that will happen in any part of your landscape, because the weather patterns and all that. If you have inadequate rainfall for 2 years, and that happens every 20 years, then your whole system's affected. Now, there are places, probably in Australia, certainly in the Southwest United States, the case where if you're in a desert environment and it's big enough, it could very well be that you'll have heavy precipitation in one part, well, relative to a desert, but no precipitation in the other part of your desert. So that could change things, and just realize. But the reason why we use that probability uniformly is we assume that adequate rainfall influences all of your system. And the sensitivity could change. The different proportions there, the 0.01, the 0.05, could reflect sensitivity of the life stage to that event, so the seedlings are more vulnerable to it. Or it actually could reflect something spatial that we're not talking about right now. So just realize that's why that's there.
Yeah, so we're creating the very simplest possible model. This is what we're representing here is an aspatial model, right? It's treating the whole landscape uniformly. And as I tried to show before, we did this because this is how we usually start these models. We like to think non-spatially first to get the basic dynamics down, and then we come back iteratively and build out more and more complexity in the spatial and temporal dynamics. So the next transition that we lifted from the conceptual model is the possibility of there being extreme drought. And so this has a much longer return interval. It's a 1 in 250 year event. But when it happens, we said in the group that there's a probability of 1 that you will transition from pole to grassland shrubland. And if you're mature, there's a 1 in 2 or 50% chance that you'll move across. So that's what's modeled in the case study we've done so far.
Colin, I'm a pest, so Colin, I'll add something to that too. The 1 by 250 is when you define extreme drought means different things to different people. And you need to define what you mean by extreme drought. In the US, the benchmark we use is that if you have 5 consecutive years where your standard precipitation evaporation index is below average for 5 continuous years, that's an extreme drought event. Having extreme drought in 1 year is not considered an extreme drought. You have to have 5 continuous years below average to be. So it's really important when you define these return intervals to actually define what you mean by severe drought or prolonged inundation or things like that.
Right. The next transition we considered, and these are all natural transitions because we're in the reference state, so you're not going to see any, we're running out of room here. There's not going to be any anthropogenic transitions in this first model, the reference model. We had prolonged flooding, which you can see the return interval here is 1 in 10 years. However, when it happens, there's a fairly low probability, and it decreased as you got more mature. But this was the probability that you would transition into a wetland. So this is a case where we're modeling a transition from one expression in one state into a different state. And we haven't, eventually we would have to define what expression it moved to in this other state, but we haven't, the model I'm showing you here today doesn't actually build out the wetland dynamics. And I think also at this time, we also added in a transition of you could move back from the wetland. Actually, this should have been an earlier, I guess. For inadequate rainfall, that 1 in 20 event, you could move back with a probability of 1. If there was inadequate rainfall, you could move from a wetland back to a seedling. And the episodic flooding is the last transition. This happens, I don't know why these two numbers are different, but they are. Well, I guess we have the probability of 1, so we kind of just inferred the net effect of the flooding on the probability. But you can see that you get the idea anyway. The numbers, as I mentioned earlier, aren't critical to the exercise. So when we're done, we have a state in transition simulation model, also a conceptual model, that looks something like this for just the reference state only. And so we can then look at what that's what I have here. It's exactly the same thing. So, I can open up any of these boxes and I can see here the transitions that I just talked about. I can actually look at them all at once here. If I go to the very end, here's a table with all the transitions in them. And so you can see, for example, let's just look at the tree growth. So that was this one here. Is my font big enough for people to see? Because I can make my screen a little bigger if you like. Is it okay, Louis and Anna? Yeah. Okay.
I can read it. It's on, but I just hit the plus and minus button.
Yeah. When I saw people saying they're hitting the plus and minus, I can hit a giant plus button on here and change the resolution if you would like it a little bigger.
That would help, Colin, to increase it a little bit.
Okay, just let me try and do
that.
Let me just. I already made it a bit bigger, but I'll go even bigger. I lose my real estate. Has that made it any bigger? It should have. If I did it right. Sometimes I don't do it. I think that is bigger, yeah, because it's a little bit bigger. So we were looking at tree growth. So here's the two tree growth transitions in the model where we say we're moving from a reference seedling to reference pole, and we have a probability of 0.25. The actual net probability is the product of this and this number here. I won't get into the details, but we said that transition can only happen when the age hits 9 or greater. And when we have it occur, we don't change the age when we move that transition. So I won't go into all the details, but on the screen here, you can basically put in all your probabilities and your pathways and define them much like I just did in the PowerPoint. So when we do that, we can simulate that model. And I've actually done that. We did that in the workshop. And I've run those already. I have them in this non-spatial. So that's this reference model. Actually, I'll just run it again so you can see. Let's just run the thing. I don't know how, I can't remember. It can't be very long.
And while it's running, I could explain, when we were doing the model originally, we did a cruder version of this that I was actually tasked to do. And people want to know, how much time did you take you to do the model? So I read the PDF documents that Anna gave me. It was an enjoyable weekend reading that. And it took me 7 minutes to build the boxes in the model and populate the transition. And it took me an hour and a half to completely populate all 4 states of the model. Of course, it was not nice. And my first simulations were pretty crappy, but it took less than half a day to do the entire thing. Then Colin went to town on it. After that, we improved the terminology because I was kind of lax on that and all that typical Louis stuff. And there you are. But so people want to know, how fast can I build a model? If you learn how to use STSim and you guys already know the ecology of the system, you can build this model like Colin did here within a day and have all your results. That's how fast you can do this.
So we get a number of outputs here. Remember, I talked about the basic outputs. So we can look at all the transitions that occurred in our simulation. And so here I have a bunch of transitions turned on, but some of them are anthropogenic. So actually, let's just save this for later because it's got more things on it than I want. But we can create a chart in the software, and there's really pretty flexible charting in here. So I can just tell it I want to graph transitions. I want to split the total area out into different transition types, and I only want to look at the transitions that are natural. So that was this, prolonged flooding, tree growth. I think that's it. And I get a chart. So I ran this simulation for 300 years. I forgot to show you how I started it. This is just a conceptual simulation of the reference conditions. I'm really just trying to see what the equilibrium, you'll see in a minute, state and expressions are under the assumptions we just made there in reference. But to do this, I set the simulation up to run for 300 years. I did 6 Monte Carlos just to get it quickly for the demonstration. I had the pathway diagram. I won't get into the details there. We already looked at it. But I told it to start with a fictitious landscape of 100 hectares. And I started all of the cells in the reference seedling with age 0. So I started everything at age 0 seedlings. I ran it out for 300 years. And I wanted to see how the model would equilibrate. And these are the transitions that it incurred. So you can see right here, because I started all the cells at age 0, when they got to be age 10, a whole bunch of them became poles. And then at age 50, a bunch of them became mature. And then onwards, the model went. So that's just an artifact of how I set up this particular simulation by not really caring about my initial conditions. But you can see there's a certain amount of prolonged flooding. It's happening at about 5% per year. It's actually, that's not 5%. That's in hectares, so it's really low. It's 0.05%. These are in percents, actually. So all these transitions are happening at fairly low levels. And that's because we had fairly low probabilities ultimately on them. But this is the kind of output you can get. You can get an idea of the variability across my 6 Monte Carlos. There isn't, that's that kind of idea. So those are my transitions. We can also look at what the thing predicted for my states. So let's just, again, probably easier if I create a chart from scratch because the other ones are set up with more states, but I can look at the area now in state class. I want to disaggregate by state classes, and I only want to include the reference ones. So let's just turn off all the non-reference. 1, 2, 4. Well, we can look at the wetland too, see what went over there. And
Colin, you may want to explain how you get to wetlands. It's actually an interesting feature.
In the model?
Yeah, I don't know if you had time to explain it. I mean, I've been on the chat when you explained it, but how do you get in SDSim to the wetland? Because it actually relates on how you do rain shifts with climate change too.
Right. So I really kind of skipped over that, but just to Louis's point, if I just close that chart for a sec, if I go back and look at the pathways, these ones here, the reference ones, you can see here, there's an arrow pointing out from this box. It's actually coming into the wetland strata over here, and I just have one wetland class at the moment. So it's coming in there. And so that's the kind of thing you can do as well as you can, I had a transition in here somewhere that moved this one here, moved me from reference mature to the wetland ecosystem type in this particular class due to prolonged flooding. So there's this opportunity again to move a cell from one, in this case, ecosystem type to another over time. And as Louis said, that's something we often do when we're modeling climate change. You might have shifts between one biophysical strata to another that occur over time. And you can easily model those using these transitions between strata. So where was that map? This is the one I was just doing, right? Yeah. So this is, again, let's just put on some variability. There isn't that much, but you can see here, I started my simulation with the entire landscape, 100 hectares in seedling, but pretty soon after that moved into pole. And then by year 100 in my simulation, I was basically down to trace amounts of seedling and pole, and I'm now in this mature state, and I get a certain amount. 1% of my landscape is projected to move into wetlands. 60% of it is projected to be in the mature state. A tiny trace is where's the rest? Did I miss some? Because that doesn't seem to add up to 100.
You've missed the grass shrub there, Colin.
Thank you. I knew there's something wrong. There's got to be a bunch of grass shrub. So yeah, so there's 15% grass shrub, 60, 70% mature, 1% wetland, et cetera, et cetera. So
Colin, instead of showing hectares, you could just shift the menu to proportion and put them on the same scale, and people will see that immediately.
yeah. So those are now proportions instead of hectares. So the point of this is that we can actually look at what the breakdown was in the last year of the simulation, because there's transient dynamics going on in here that I'm not that interested in. But I have a chart. Well, actually, let's just take this one, the one I have here. I can look at we can turn it into a column chart. Just look at the last time step 300. And look at the distribution. And so this is what the model is predicting. I would interpret this as the equilibrium distribution of expressions within the reference state for a reference-only model in floodplains. Now, this could be right, this could be wrong, but typically what we would do is we would look for data that we have, wherever that comes from, on what we believe the reference state was in this landscape, and we compare it to this, and that gives us some indication of whether the probabilities we put in are realistic or not. But the probabilities that we did put in lead to a projection of this for the landscape.
In the American literature, including me and Landfire, this was called the natural range of variability. It's not a very good term for it, but many people, I don't know why it was done. It was referred to as the natural range of variability. When you think about it, that's not what you probably mean by that. But if you see that in the literature, NRV, natural range, this is exactly what Colin is showing right there.
Yeah, so this is how far we got in the workshop 2 weeks ago, as we had this model going. With these preliminary numbers that people educated, but we were forcing them to move along, and you had 1 minute or less to come up with a number. So, but that's what you can do with the model, and for reference, right? And this is aspatial. Any questions at this point before I sort of add in the anthropogenic transitions, and as a result, the other 3 states? Make the model quite a bit more complicated in a minute. We're good? Okay, so I will, what I did next, and this is what I did a couple nights ago, because this is where we left off in our workshop together, is I created a alternative set of transition pathways where I tried to replicate this, all of this. So as Anna pointed out, the expressions within the invaded reduced canopy and the invaded mature states are similar, if not identical, to those in the reference. The halophytic state has different expressions, but by copying and pasting, I could create a replicate of this. Now they should have different probabilities on some of these things. But the important thing that I had to do here was try and introduce all these transitions that moved you from one state to another. So things like logging, these stressors, we have livestock grazing, overgrazing. There was salinity, although I didn't put the salinization in there. But you'll see what I added in a minute. So that was, and again, this is just me now, not even with Louis, 2 nights ago, just trying to put it in to give you an idea. So don't pay any attention to the numbers. But I printed up.
Can I add something, Colin?
What's that?
Something that's, can I add something here?
Sure.
When we do our model, this is something you guys may want to think about one day. Once we've shown you this model, it would be a good idea, as we suggested during the training a few weeks ago, to just throw it away and do your own model. But we go from a reference class to an invaded class, yet there's no disturbance called exotic species invasion, because you confound the degradation process with the invasion process. What that would mean is that you have missing boxes in this model. It means the way the model is done, that Colin did it, we did it previously, it means that your reference system is actually not a reference system anymore. It means a seed bank is completely invaded by non-natives. So in reality, in the real world, that you have a hard time mapping, that's the problem here. You have a reference state, plus a seed bank that is invaded that you cannot perhaps see without doing soil samples, and then there's an invaded state. So Colin and I would argue there's actually 5 boxes missing between the reference and the invaded. And if you had those boxes, you can actually decouple the invasion process from the degradation process.
Right.
And that's just a note that we're not going to do that, but you guys may want to think about that.
Right. So we were trying to be as true as we could to the conceptual diagrams and not want to go off of them. So let me just give you an example of what the transitions look like. So I added in let's look at logging. It's a simple one. So here's just the logging transitions that I added. So the logging transition, if you look at it in here and we look at logging, we set its probability to 1 because I'm going to go set the amount of logging I want to happen on the landscape somewhere else. I'll show it to you in a minute. So I just zeroed that out by putting a 1. But basically I said logging can only happen when you're 50 years old or older. So it's only mature trees. But when it happens after a logging transition, your age is going to be set back 20 years. I assume this was some form of selective logging. So that's kind of the dynamic I have in there for logging, right? And so you can see those logging transitions are happening just out of these 2 mature classes, and also they can happen within the mature class. A mature class can get logged and set its age back without actually changing expressions. So that's one example. Let me just show another one. What does grazing look like? Grazing generally looks like it degraded you. So if you're in these reference states, for example, you're a mature reference, mature reference condition, and you had grazing occur. Here it is here. You moved into stayed mature. Your age didn't change, but you moved into this invaded state with the same expression. So really what the grazing is doing is shifting everything down from the good stuff into the invaded stuff down here, right? And things that are already invaded just stay as themselves. They can't become more invaded. That's kind of the idea with grazing. And we have some other ones in there as well. I mean, there was grazing, logging. I think I had nutrient input was very similar to the grazing. It degraded you from reference into other conditions. So on and so forth. So this is just trying to represent everything we saw in the diagram. And so those transitions are all in there now. So the full suite of transitions that were in those conceptual diagrams are now in this model. The challenge, of course, was putting some numbers on these, right? And so what I did is, just to get things running, you'd have to spend some time deciding on the rates of these. But if we look over here, let's just go to the end. I think, I set them on a different screen. So I set them all, actually, they're not here. Let me just go look where they are.
And you set them to 1 and use a temporal multiplier, the transition multiplier, to actually introduce them.
Right. So what I did is, for all those pathways that were anthropogenic, as Louis said, I just set the probability to 1. And on a different screen, I went and globally set them. It's just an easier way. We have these things called multipliers that those that were in the course will know about. But it's a way to change probabilities in groups. But so here is the scenario that I set up for the anthropogenic. So what I did is I set the grazing to, I set everything to be roughly hitting 1% of the landscape per year. And I came up with that number because I thought, well, okay, your landscape, I looked online and there was some water legislation. I can't remember what it was, but there's clearly some flood control measures that went in around 1920 or so, about 100 years ago. So it's probably being slowly degraded from reference for 100 years roughly. So I will assume that 1% per year is being degraded. That's how I came up with these numbers, nothing more than that. But it's just, again, to get the model sort of up and running. So you'll see grazing is happening at 1% per year. Nutrient input each cell has a probability of 0.01 per year. This river regulation, which had certain effects, had 1% per year. And the logging I bumped up to 1.5% per year because it was only acting on the age 50 and older. So I bumped it up so its net effect, as you'll see in a minute, was about 1% of the total area logged per year. Okay, so that's how I set those transitions. I won't worry too much about the recovery ones. I turned off the salinization and the soil flushing, which is a way to bring things back after being, going into this through the salinization. So I just turned that off because I had enough on my hands already dealing with the transitions that you see here. And so I can do a run with that, and I've done that already. And so that's this managed one. I've run it already. I'm just going to look at the results. So what you can do here now is we can look now at the transitions again. I've got the reference and this managed. Both of them I ran with this sort of make-believe 300-year simulation, again, starting all, I think, in reference to begin with in the youngest. But if I scroll down here, why are these off the screen? There. Scroll down. There's all the transitions. So now I'm going to have to look at them all. I hope there's room on your screen. Okay, so here I've got the same graphs I showed before of the area transitions per year. And the blue is the reference simulation I showed you before. So you can see there's 0 grazing, 0 logging, 0 nutrient input, and 0 river regulation in the reference. But this managed simulation now has the same level of natural disturbance, but it's added, as you can see, about 1 hectare per year on a 100-hectare landscape of grazing, of logging, of nutrient input, and of river regulation. So just some kind of base to look at. And so that's the simulation we've just set up. We're comparing the two. And now I can go and look and see what this means for, in full detail. I think this is going to be too much on the screen for you because I know it barely fit for me before. But, we can customize this in a sec. This, you can see it sort of. This is all of the possible expressions that I'm tracking in my model. At least I'm not showing the halophytic ones because I'm not showing salinization in here. But you can see, and the details don't matter. Again, I can't see it on my screen. But I can now predict, and I can put variability on here too, the fate of every state and expression over time. But just to look at it a little easier, let's just I've summarized, created another chart here, custom chart, that just looks at the area in each state. So I aggregated things up into the states rather than looking at the expressions. So again, both simulations started with the entire landscape in year 0 in reference. Of course, the blue scenario moved things around amongst expressions, but kept it in reference the whole time. And we can see that with these anthropogenic transitions, disturbances added to the model at the rates I put them in at, the software, the model predicts that about 25% of our landscape should be in this invaded mature, whatever this is. 60% in the invaded reduced, and 16% in reference. So that's again the kind of thing that you can do with this model now. Now we have a functioning model with all of the transitions in it. And we can do a bunch of other things with them. Now what I did is I just did I'm going to take these two off. I just played around a little bit with this the other night. And I said, what if we did a run where I spun up the model, I think for 200 years to get to that equilibrium reference state. Then I ran it for 100 years under the historical management, like I just showed you. Whether that's a correct representation or not, I don't know, but we ran it for the last 100 years up till today. And then we ran it forward another 100 years where we reduced the logging, grazing, and nutrients by 50%. And then I did another scenario where I did the same thing up until supposedly today, and then I reduced the logging, grazing, and nutrients by 100%. And I can compare those to a run where I run it under the historical regime for 100 years and then another 100 years. So these are three sort of what ifs, and to start sort of exploring scenarios of future changes in management. So let's just take a look at what that gives us. Again, I won't go into all the details of the expression. Let's just look at the sort of summary of what that looks like across the states. So now what's going on? That's not right. Did I run those? Should be looking at, let me just see.
What about if you pick states?
I haven't gone out far enough. That's what it is. It's
Oh, okay.
They're all the same point. They haven't changed. In fact, we should get rid of the first 200 years then in these simulations was the spin up of my reference to get it the proper distribution of expressions. So let's just drop the first 200 years because that's really a spin up. And then we'll say, okay, now we're looking, year 200 is really now 100 years ago when we were all reference. And so for 100 years, we lost most of that reference state, right? And then that brings us up to today where we have no reference. And then we have these three scenarios. Let me just show the legends. The blue is business as usual. The red is where we reduce the stressors by 50%. And the green is where their stressors were set to 0. And so, again, these don't pay attention to the numbers, but the idea is here that you could start exploring different alternatives for sort of future levels of different transitions that you can actually control in your model. The last thing I wanted to show you is this is all a non-spatial sort of toy model. The one thing I wanted to do, I did just this morning, is I wanted to give you a sense of how you would run this spatially. Now, we're nowhere near being able to do that, but I created a spatial simulation just to give you an idea. So what that involved doing then is I have one scenario in here. I'm going to look at this one. I'm running out of time. And so this is a scenario where I started the model in 2015. I ran it just for 10 years. I used the same pathway diagram and probabilities that I've showed you so far. But for the initial conditions now, I brought in a raster that Anna gave me that showed me what the state and expression was of every cell in 2015. I could also infer the strata. So I have the initial state and expression of every cell from a raster. I didn't have the age, so I actually randomized the ages non-spatially. So I basically told the model briefly that I want you to randomize the age over the range of possible ages for every state class, just a subtle little thing that I did. And then I ran the model out for 10 years using that historical regime. Now, I'm going to add those to the results. That was run probably took, I think it took about 10 minutes to do. We can look at the output just so you get an idea of what you can do here. So this is the transitions now. So this is an example of the kind of output you can get spatially. So I'm showing you here maps of, actually, I don't know why it's zoomed in. Here's the whole study area. Actually, it's better if I show you the study area first. So let me bring up let's just create a new map like this. So this is a map. Let's look at the ecosystem type. So let's just look at and this is let's just look in the starting year, 2015. So this is a map of, oh, that's interesting. It's changed. Huh. Wasn't expecting it to change so much. So this is a map of the expressions in 2015 and 2025. Let's just look at the beginning and the end. So here are my expressions. This is just a straight input. It's just a record of the input, but you can, in the software, you can do this. And I've generated what the expressions look like in 2025. And we can already see that the model is projecting a loss of wetlands. I can see that here. If I zoom in on that, you can sort of see in here, it's not doing the loss of wetlands very intelligently. I didn't give it any spatial dynamics to it. I just ran that non-spatial model, but it's slowly losing wetlands over time. In fact, I can probably look at the whole time series, 2025. It's going to take us, so we can sort of slowly see over time the loss of wetlands. We can look also at, as I had here, we can look at the expressions. So I can get a map here of the expressions. I've colored them where green, there's the wetlands in blue. The green is reference. There's very little reference in 2015. And the red is invaded, where the paler red is the reduced. But again, you know the details aren't important, but the software allows you to generate maps like this over time, including the projections out to 2025. So you can project that spatially. And you can also look at your transition spatially. So for example, here I show the logging. This is the logging this is all for one Monte Carlo. I ran 6 of them, but I'm only showing 1 of them. So this is, again, a pattern of the transitions as I model them. So that's the end of my presentation. I'm happy to stay on if people have questions. I realize I've gone to the end, but questions and discussions, I'm happy to continue, please. Louis, do you have anything you want to add?
No, I was going to point out in the maps that some things didn't change. You'll have noticed that the ecosystems for which we did not populate with transitions and all that didn't change, just because we didn't provide any change possible. So that's why I think it was the red or brown things just didn't change, because there's actually no underlying transitions in them. We didn't model those. We only modeled the wetland and the floodplain.
That's right.
And those are the only things that should be changing in the landscape.
And the wetlands, because of the change from.
Yeah, they bounce off of one another through that to-from ecosystem transition in the model.
Yeah.
I did have a comment to make, is that, and this is something we talked about at the workshop, but in the document, and please interpret this the good way, the mature floodplain forest should be 95% of the area, and Colin and I are never been able to reproduce that. We got up to 60%, maybe in one case 75%. It's highly dependent on your flood regime and other assumptions, and it actually would be dependent on spatial layers introduced, like the deeper pools and all that. But there is a discrepancy between what the model can predict and what you guys think it is. And that's actually an interesting question of why is that happening, to reconcile. And I actually, given the dynamics of this model and the return interval for prolonged flooding and all that, and inadequate rainfall. I would be hard pressed to believe that you could get 95% of the floodplain in mature forests. The dynamics are just too rapid for that. You have too many chances of producing seedlings and poles and all that to actually be there. So that's something, in some ways, Colin and I are just doing the model. We don't, we're not emotionally attached to this, but, or even scientifically actually, because it's not our system, but you guys may want to think about it. And I think that's an interesting result, that there's a discrepancy right there.
You know, the other
thing, from scientific terms.
The other thing I noticed as well when I was doing this is the first model. I mean, all our models have been in North America, but every model I've done pretty much of a landscape like this has had fire in it, and this one is the first model I've done without fire. So I don't know if fire is not, not present or not important. I mean, there are, but it was just another thing I noticed. I see one question here. Is there a way to incorporate validation data to fit a model through a given point or points? That's a good question. That's I don't know, Louis, how much you do with that, but I know on other projects we do a lot of that. We do what are called we call them retrospective simulations, and actually Anna gave me data for 2010 and 2015 here, and usually the first place we would start is we would run our model. Starting in we do a retrospective run where we start in 2010 and make sure we can reproduce what we observed in 2015. Now there are different techniques for doing that. I won't get into it, but in principle, fitting the probabilities, the transition probabilities to your historical data is a huge part of this modeling. It's a very, very empirical approach. We're extremely data driven in this kind of environment. You can use models. Sometimes people use process models to generate the probabilities that then get fed into here. But we always seem to be coming back to making sure that the dynamics we get fit the data we have. So yeah, that's a big point, a big part of what we do with the model.
I would agree with Colin entirely on that. Also, when I do some simulation, actually, I wanted to add, this is also the first model I've ever done where there's no fire in it. I have a hard time believing that, given all the international news coming out of Australia about the whole country burning up. But it's this is actually an interesting, I would say, refreshing case, because it's actually not burning. But one thing we do in our models, especially the ones that have fire with them, there's certain classes that have a tendency to explode, and they're kind of explode to what they should, the area, their extent explodes. And they're kind of cryptic classes that you typically don't pay attention to, that are in your model, because they're not the focal classes. Now, this would be the expressions for you guys. And then suddenly you start exploring your data and you realize, holy cow, I have early successional shrub dominating the whole landscape at 25% because of, let's say, grazing or something like that, livestock grazing that's a little bit too intense. Well, we have, since the Taylor Grazing Act of 1947, we've never achieved that, even under the worst conditions. So it tells me immediately there's something wrong with the model. So we do a lot of checking like that, and it really pays. But what Colin said is actually pretty darn important, to try to reproduce the past up to a point to make sure that your model works.
Any other, stop sharing so I can see the screen a little better. Anything else before I sign off? Anna, do you want to add anything before?
Oh, I just wanted to say thanks, Colin. It was great to see those extra simulations that you've done since I saw the model a few weeks ago. That was really great. And I think one of the key points is you can start to test your hypotheses. It's a really, I guess, an important use of the tool, as well as the prediction, is starting to think about what hypotheses you've got embedded in your state and transition models or other models, and are they, how can you, do they need some tweaking? I think that's really great.